Okay. So 11.7 is titled Strategies for Testing Series. Okay, and again, it's really just choosing the correct test for the correct series. Okay, so if we have something that's geometric, then we'll choose a geometric test. Okay, absolute value of r is less than 1, converges, otherwise it diverges. Okay, if it's harmonic, then we know that diverges, and that's the summation n equals 1 to 1 over n. The divergence test is for any series whose terms do not get smaller, do not go to 0. Okay, the integral test, if we can take the integral and we can show that that integral converges, then the series converges, or if we can show that that integral diverges, 1 to infinity, then the series will diverge. Okay, number 5, the basic comparison test, if we get something that converges, okay, and b sub n is greater than greater than or equal to a sub n, if b sub n converges, then a sub n would converge. Okay, if a sub n diverges, okay, and it's smaller, then b sub n would also have to diverge. Okay, the limit comparison test, if we have a sub n and b sub n, then the limit as n goes to infinity of a sub n over b sub n okay, if that's a positive constant, then they either both converge or they both diverge. Okay, the alternating series test, if the series alternates and every term of the series, the absolute values are decreasing, and that decreasing series goes to 0, then it diverges, regardless of how fast it goes down. Okay, so the alternating harmonic series converges, but the harmonic series itself diverges. Okay. Number 8, P series for the summation of 1 over n to the p. If p is greater than 1, then it converges. If the power is greater than 1, then it converges. If the power is less than or equal to 1, then it diverges. And then we have the ratio test. The limit as the absolute value of a sub n plus 1 over a sub n is equal to L. If that's less than 1, it converges. If it's greater than 1, it diverges. And if it is equal to 1, it's inconclusive and you need to use another test. Okay, the root test is the limit as n goes to infinity of the nth root of the absolute value of a sub n. Okay, if that is greater than or less than 1, it converges. If it's greater than 1, it's diverges, and if it equals 1, it's inconclusive. Right? Okay, and this was all from last time we finished up our 10 tests. Okay. Okay, so let's look at and answer the question. We're not going to necessarily find the whether these converge or diverge and go through all the work, but I do want to set up and say which test would I use for each of these series. Okay, which test should be used for okay, the summation n equals 1 to infinity of n minus 1 over 2n plus 1. Any idea on what test we should use for this?
Divergent test.
Yeah, we would want to use the divergence test because the limit here is going to 1/2. It is not going to 0. Okay, so this diverges. We want the divergence test here. Okay, because we have an asymptote for the terms, and the terms the terms themselves are converging to 1/2. The series is going off to infinity because you're just you're adding 1/2 basically each time. Okay. Okay, B. We have n equals 1 to infinity of n cubed plus 1 square root over 3n cubed plus 4n squared plus 2. Okay, so now this test might not be obvious at first glance, but we can actually use the limit comparison test on this. Okay, so if I just take the first terms of this, I would take the square root of n cubed over 3n cubed. Then this equals n to the 3/2 over 3n to the 3rd, which is equal to 1 over 3n to the 3/2. Okay, and this thing is a p-series, which converges. Okay, if we were to compare, oops. Okay, and then I wouldn't want to use the basic comparison test on this because I don't really know, if this thing is going to be, less than for all of the terms, and I don't know, it would have to be, for the original one to converge it, every single term would have to be less than the one that I'm comparing to, if it's a convergent series. And so I don't really know that because that n cubed plus 1 and the plus 1 is under the square root, and then I've got these extra terms on the bottom. Don't really know if it's going to be, if a sub n, which is my first one, is really going to be less than, but I can create a ratio here of these two and use the limit comparison test. Okay, on that one. Okay, C. Okay, the summation of n equals 1 to infinity of n e to the negative n squared. So this one's interesting. Okay, any ideas what I'd want to use here?
You should put the e to the something downstairs to have a positive exponent.
Yeah, I mean, you could bring that down. There is one test that would work fairly well, and that's if I were to integrate and do a u sub.
Integral test.
Yeah, the integral test, exactly. So we're going to do integral test on this one. Okay, since the integral of x e to the negative x squared is easily integrable, because it's not even integration by parts. It's just a basic u sub with u is equal to negative x squared. Okay, so we could get a nice u sub out of that guy. Okay, D is summation n equals 1 to infinity of negative 1 to the nth power n cubed over n to the fourth plus 1. Okay, what would we want to do here?
Alternative series test.
Yeah, alternating series test. This alternates, the terms do go to 0, but they go really slowly. Okay, but even though they go really slowly, like the harmonic does, it's still going to converge because it alternates. Okay. Okay, E. Okay, summation n equals 1 to infinity of 1 over 2 plus 3 to the nth power. Okay. What could I do with this one?
Divergent test.
It actually converges. So that divergence test wouldn't help us because the limit of this thing goes to 0. Okay, but good guess. Okay, well, if we had this guy here, 1 over 3 to the n, aren't all the terms of this guy less than? So we could do a comparison test on this, right? So we could do a basic comparison test. Okay, but then how do we know that this guy is convergent? Any ideas? What if I rewrote it a little differently?
Oh, it's geometric series.
Yeah, it's geometric. So, so this guy is geometric. Okay, which we know converges if r is less than 1, and r in this case is 1/3. Okay, so that I know converges, and then I can compare it, do basic comparison test. Okay, basic comparison test with this guy, which is always smaller than something that I know that already converges. Okay. Okay, what about F here? Okay, F is n equals 1 to infinity of 2 to the n over n factorial.
Ratio test.
Yeah, ratio test, that factorial, use a ratio test. Okay, since we have a factorial. Okay, if you have a factorial, it screams ratio test because if you get n factorial over n plus 1 factorial, then everything cancels out except for the n plus 1. Let me show you that real quick. Okay, let's do F here. The limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial all over 2 to the n over n factorial equals the limit as n goes to infinity, okay, of 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the nth power. Okay, this is equal to, okay, 2 to the n plus 1 over 2 to the n. Okay, that's just going to leave me at 2. This is the limit as n goes to infinity of 2. And then n plus 1 factorial is all the numbers multiplied up to n plus 1. And that's going to, and so I would get an n plus 1 times n minus 1 all the way to 1. And on the top, I would get n times n minus 1, okay, all the way to 1, all the way to 2 times 1, blah, blah. And everything's going to cancel all the way up to n. And so this equals the limit as n goes to infinity of 2 over n plus 1. Okay, well, that's just 0, which is less than 1. And so therefore, the series is convergent. 2 to the n over n factorial is convergent. Okay. And that is basically 11.7. Okay. Okay, let's transition now to 11.8. Okay, where we get to introduce power series. Okay, so power series are series like we've done. They just have an x component now. Okay, 11.8, they're functions of x. Okay, series that involve x. Okay, 11.8 is on power series. The power series are of a certain form. If they're centered at 0, then they look like this, and they start at 0. N equals 0 to infinity of c to the n, which is some constant, okay, x to the n, okay, where we now have an x variable raised to the nth power. And this is equal to c naught, okay, or the constant, the 0th constant, plus c1, first constant, times x, plus c2, x squared, plus c3, I'll do one more, c3, x cubed, plus dot, 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 plus cn, x to the nth. Okay, so, okay, and then it continues on, it goes on forever. Okay. C to infinity, x to infinity. Okay, if it's centered at a, okay, it's centered around a value a, then this changes slightly. We still start with n equals 0 to infinity of cm, but now we have x minus a to the nth power, okay, which is going to become c naught plus c1, okay, x minus a plus c2, x minus a squared plus c3, x minus a cubed plus dot, 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 plus cn, x minus a to the nth plus, and then again, it just goes on forever. Okay, so let's look at a power series. Okay, let's look at and ask ourselves, for what values of x does the series summation n equals 0 to infinity of n factorial x to the nth converge? Okay, for what values x does this converge? Okay, so because not all the values for x will make this converge. Okay, so x could be 2, it may not converge. If x is 1/2, it may converge. Okay, so for what values of x does this thing converge? Okay, so when we want to test power series, we use the ratio test. Okay, it's the one that is the most convenient for us to use. Okay. So use ratio test. Okay. Okay, and in doing so, using the ratio test, it always leaves us with 1x. Okay, which is nice. So we're gonna take the limit as n goes to infinity of n plus 1 factorial x to the n plus 1 all over n factorial x to the nth. Okay, and when does this converge? It converges when this is less than 1. So I'm going to plug in the condition for convergence, okay, is less than 1, because I'm actually going to end up having to solve for x. Okay, so the limit as n goes to infinity of, we just saw that n plus 1 factorial over n factorial, everything's going to cancel out except for the n plus 1. So that's n plus 1 times x to the n plus 1 over x to the n. Everything's going to cancel out. The x to the n cancels. And I'm just left with x to the first power, which is just x. That's less. When is that less than 1? Okay, I'm gonna break up the absolute value here. The limit as n goes to infinity of the absolute value of n plus 1 times the absolute value of x is less than 1. Okay, because I don't need absolute value of n plus 1. Why? Because we're starting at 0 and we're going to infinity. So n equals 0 to infinity, positive infinity, and so we can remove the absolute value bars. We have the limit as n goes to infinity of n plus 1 times the absolute value of x is less than 1. Now, this thing, n plus 1, that goes to infinity. Okay? And so you might think, well, this will go to infinity regardless of what x is. And that would be correct, except for one value of x. Okay, the only value of x where this thing doesn't go to infinity is when x is 0. Okay, so we say that this is diverges for all values of x except, because this thing's going to go to infinity. Okay, or just kept getting bigger and bigger numbers. Okay, but when x is 0, then it converges because the 0 multiplied by a number, 0 times a number is just going to be 0, which is less than 1. Okay, diverges for all values of x except x equals 0. Okay, then it converges. Okay, but then it's kind of a trivial case. When x equals 0, we really don't have a power series. We just have a series of zeros, which would add up to 0. So it's kind of a trivial case. Right? Okay, let's do one that's a little less trivial. Okay, number 2. For what values does the series n equals 1 to infinity of x minus 3 to the nth over n factorial, or no, not factorial, just n, over n converge? Okay, so let's look at that. That's power series centered around 3. Okay, you could write it as 1 over n times x minus 3 to the nth, but it's all good. And it doesn't matter if we're starting at 1 or 0. We could always back out one term and subtract it off. And it's either going to converge or it's going to diverge because we're going off to infinity. We're adding an infinite number of terms. Okay, so so again, use the ratio test. The limit as n goes to infinity of x minus 3 to the n plus 1 over n plus 1 over x minus 3 to the n over n. Okay, so we've got a complex fraction. Okay, when is this thing less than 1 is the question. Because it does converge if we can get values that are less than 1. If there are x values, which x values produce an inequality that's less than 1? Okay, so let's turn the division into multiplication. Limit as n goes to infinity of x minus 3 to the n plus 1 over n plus 1 times n over x minus 3 to the n. It's less than 1. Okay, so this becomes the limit as n goes to infinity of, I'm going to put the n over the n plus 1. Okay, and then x minus 3 to the n plus 1 divided by x minus 3 is, to the nth is just x minus 3. Okay, it's less than 1. I can bring the n over n plus 1 outside the absolute values because that's always going to be positive. So this is the limit as n goes to infinity of n over n plus 1 times the absolute value of x minus 3 is less than 1. And what is the limit of n over n plus 1? What does that go to? Limit as n goes to infinity of n over n plus 1. Okay, well, you can do some algebra on that, or you can just use L'Hopital's rule, and it becomes 1 over 1. And so this thing will go to 1. And that's the only thing that the limit is acting on is the n. It doesn't act on the x value. Okay, the x variable. And so this is just absolute value of x minus 3. When is absolute value of x minus 3 less than 1? Well, that's a compound inequality. This is my and statement. Negative 1 is less than x minus 3, which is less than 1. If I add 3, I get 2 is less than x, which is less than 4. And so this is my, so any number between 2 and 4 is going to converge. Okay, any number between 2 and 4, okay, will cause the series to converge. To converge. Okay, but, and here's the big but, Okay, but what about what happens at the endpoints? At 2 or 4. Okay, but what happens at 2 or 4? Okay. Well, let's see. Let's see what happens. Okay. If I test the endpoints, okay, and I plug back in, this is x minus 3, right? So x minus 3 to the n over n, right? When n is equal to 1 to infinity. So for 2, when we plug in, we get 2 minus 3 to the nth over n, which is equal to the series -1 to the nth over n, which is the alternating harmonic, which converges by the alternating series test. Okay, so we get convergence by the alternating series test. Okay, that's the alternating harmonic. Okay, so this guy too converges. Okay, what about 4? Let's test for 4. For 4, we get 4 minus 3 to the nth power over n, which becomes 1 to the nth power, but 1 to the nth power is just, okay, so that's 1 over n, which is divergence. It diverges by harmonic series. Okay, and so 4 diverges. So for what values does this thing converge? That's what the original question was. So it converges for 2 is less than or equal to x, which is less than 4. Any number between 2 and 4, 2 is included, but 4 is not included. Okay, and we call this thing the interval of convergence. Okay, so we have an interval of convergence. Okay, of 2 to 4. Okay, you can write it algebraically like that. You could write it using interval notation as well. It really doesn't matter. Okay, so either way. Okay, let's do number 3 here. Okay, find the domain of the function defined by j naught of x is equal to the sum of n equals 0 to infinity of the -1 to the nth power, x to the 2nth power, all over 2 to the 2n times n factorial squared. Geez, that's a lot. Okay, so let's look at all of this. So again, ratio test. Okay, and we only have a domain for x if this thing converges. If it doesn't converge, then you're not gonna have a function of x. Okay. So where does this thing converge? Let's do the ratio test on this. The limit as n goes to infinity of, this one's gonna be a big one. Okay, -1 to the n plus 1, x to the 2 times n plus 1, all over 2 to the 2 times n plus 1. Okay. And this is n plus 1 factorial squared. Okay, all over the original, which is -1 to the n, x to the 2n, all over 2 to the 2n, n factorial. Okay. That's equal to the limit. Oh, no, sorry. And that has to be less than 1. Okay, so this is equal to the limit as n goes to infinity. I'm just going to flip everything upside down. That is underneath my second fraction. Okay, -1 to the n plus 1, x to the 2. I'm going to distribute this 2n plus 2. Okay, all over 2 to the 2n plus 2. And this is n plus 1 factorial squared times 2 to the 2n, n factorial over -1 to the nth, x to the 2n. Again, where is that less than 1? Okay. So the -1 to the n plus 1 and the -1 to the n, those are going to cancel and just leave me with a -1. Okay, so that's just going to give me -1. Okay, the x to the 2n plus 2 and the x to the 2n, that's just going to cancel the 2n's and leave me with an x squared. That's cool. Okay, the same thing with the bottom, the 2n, 2 to the 2n and the 2 to the 2n plus 2, that's going to just cancel and leave me a 2 squared, which is 4 on the bottom. I'll leave it as 2 squared right now. Okay, times, I'm going to, oh, so this was n factorial squared. My bad. Okay, this, I'm going to combine the n factorial over the n plus 1 factorial squared less than 1. That's the limit as n goes to infinity. Okay, and so the n factorial over n plus 1 factorial, well, that just cancels everything that would have been factorial and leaves me with n plus 1. So in total, okay, I'm left with the absolute value of -1/4, okay, x squared all over n plus 1 squared. I want to find out, well, when is that thing less than 1 as the limit as n goes to infinity? Well, this thing will go to 0 regardless of what x is. You could plug in any value for x, and it's always going to go to 0 because I'm always dividing by n plus 1. And so the limit as this thing, that goes to 0. And since 0 is always less than 1, okay, so that's always true, then I can use any value for x. Okay, and so this converges for all x values. And so the domain of j naught of x is equal to, for that function, is -infinity to infinity. It converges for everything. Okay, let's look at a couple of rules here. Okay. Theorem. For a given power series, summation as n equals 0 to infinity of c to the n of x minus a to the nth power. Okay, and if it's centered at 0, then a is just 0. So this is just your generic power series. Okay, there are only three possibilities. Okay, number one, the series converges only when x equals a, or basically at 0. Okay, you know, when we're just adding up zeros. Okay, if you plug in a for x, you're going to get 0, and so you're just going to add up a sum of zeros, which is 0. It converges, all right, but it's basically, it's trivial. Okay. Okay, number two, the series converges for all x. Okay, basically, like we saw in the last one, you know, our x can be anything we want, negative infinity to infinity. Okay, and number three, the series converges for, or say when the absolute value of x minus a is less than r, okay, for some positive r, and diverges for x minus a is greater than r. Okay, where r is referred to as, I think referred only has one r. Okay, referred to as the radius of convergence. Okay, so radius of convergence. Okay, so we're saying we're going to get to a place where we have absolute value of x minus a, okay, is less than r. Okay, and so it's going to converge, okay, for absolute value of x minus a is less than r, and diverge for absolute value of x minus a is greater than r. Okay, and then what happens if it equals r? We have to test the endpoints. Okay, if it equals r. Okay. Okay, so very much like we did in example 2, where we ended up with, I think it was x minus 1, was it? No, x minus 3 is less than 1. That gave me that, so the radius of convergence here is 1. So r is equal to 1. This is from example 2. Okay, and so all the values, absolute value of x minus 3, less than 1, okay, it converges. Okay, all the values for x that satisfy this converge, absolute value of x minus 3 greater than 1, it diverges. Okay. So it converges this. And then if I take absolute value of x minus 3 equals 1, which is what the endpoints are, okay, we need to test independently. Okay, test them independently. Okay, which is what we did. We tested 2 and 4. Okay, so let's do another one of those. Okay, number 4.
I have a question,
Yeah.
Professor. Yeah. How can we get R equals 1 from example 2?
Yeah, so if we look back at example 2, okay, we came out with this guy here. And so the radius of convergence is 1. Think of it like on a number line. Okay, we're going from 2 to 3 to 4, right? And so what happens at 2 is I have 2 is included, 4 is not included. But what's the radius? Think of this, like a circle, right? What's the absolute value? What's the distance of the radius here? Okay.
Okay, got it.
It's 1, right? It's 1.
Yeah,
And so, I can make a little Pokeball,
got it.
but
Thank you.
yeah, so I'm just kidding about the Pokeball, sorry. Okay. So the radius, you think of it as a radius, but it's really just a radius in one dimension. Okay, it's a one-dimension radius, which is just distance. So, and so it's 1. So the radii is 1. Okay. Okay, number 4. Okay, find the radius of convergence and interval of convergence okay, radius of convergence and interval of convergence okay, which is just the domain of x for the power series okay, n equals 0 to infinity of -3 to the nth, x to the nth, all over the square root of n plus 1. Okay, so let's find out, when is this thing going to converge, and does it have a radius of convergence? And what is that radius of convergence? Okay. Okay, so again, ratio test, limit as n goes to infinity of -3 to the n plus 1th power, x to the n plus 1 power, all over the square root of n plus 1 plus 1. Okay. All over -3 to the nth power, x to the nth power, all over the square root of n plus 1. Okay. Okay, let's flip this over. That's less than 1 if it converges. Okay, and so this becomes -3 to the n plus 1, x to the n plus 1, all over the square root of n plus 2, n plus 2 times square root of n plus 1 all over negative 3 to the n. This should be in parentheses. Okay, x to the n. Okay, good, good, good. Okay, so the negative 3's are going to cancel and just leave me with a negative 3 on top. The x's will cancel, leaving me with an x on top. Okay, so that's gone and that's gone. Okay, and then I'm going to rewrite this as the square root of n plus 1 over n plus 2. Okay, is less than 1. So I get the limit as n goes to infinity of that guy. Okay. Okay, and so the limit as n goes to infinity of this guy here, again, this is positive. Everything there is positive, so I can bring that outside. All the n's. What I'm talking about is this right here. Okay, that's going to always be positive because everything's positive in there. So I could bring that outside and just deal with the limit. So the limit as n goes to infinity of the square root of n plus 1 over n plus 2, negative 3x, okay, is less than 1. Nice. Okay, well, what is the limit of this thing? Well, the limit of that is just 1. It just ends up being 1 over 1. The square root of 1 is 1. And so this thing all goes to 1. Okay. And so we're just really left with the absolute value of negative 3x. Well, again, I can split this up. Absolute value of 3, negative 3 times the absolute value of x is less than 1. Okay, and so this is going to be 3 times the absolute value of x is less than 1. Divide by 3, and we get absolute value of x is less than 1/3. So what's the radius of convergence? What's r? I mean, if I can write it like this, x minus 0, this is centered at 0. Okay, if you want to compare it to x minus a is less than r, right? Then the radius of convergence here, okay, is 1/3. Okay, so we have this guy here that tells me that the radius of convergence okay is r equals 1/3. Okay, so that's one answer. Okay, now I need to find the interval of convergence. Okay, the interval of convergence, okay, is gonna, I'm gonna have to figure out, well, for what values, okay, does this correspond to? Okay, and that is a negative 1/3 is less than x, which is less than 1/3. And so this isn't my true interval because what do I have to do? Okay, that gives me, 99.9% of my values. But what's in question? What's in question are the endpoints. That's what's in question. Okay, the value negative 1/3 and 1/3. We want to know, okay, it converges. Okay, if we look at the number line, negative 1/3, the center is at 0, and then we have 1/3. So the radius of convergence is 1/3, okay, because again, think of it like a circle. Okay, but what's in question are the endpoints themselves. So we need to know, okay, well, what happens at the endpoints? We need to test x equals negative 1/3 and x equals 1/3. And how do we test that? We plug it back into the original series and see if the series converge or not. Okay, so what was the original series? The original series was, power series was n equals 0 to infinity of -3 to the nth power, okay, x to the nth, all over the square root of n plus 1. Okay. Okay, so let's plug in, let's test -1/3. We'll see what happens here. Okay. So if I plug in -1/3, I get n equals 0 to infinity of -3 to the nth times -1/3 to the nth, all over the square root of n plus 1. Okay. Nice. Okay, and so well, those cancel. I mean, I could rewrite this as okay, n equals 0, infinity of -3 times -1/3 to the nth power over n plus 1, which is going to be 1 to the nth power, which is just 1. So this equals the summation n equals 0 to infinity of 1 over the square root of n plus 1. Okay, so does that guy converge or diverge? Anybody have a test that I might be able to use to see if this converges or diverges? Any guesses?
Divergent.
Yeah, why? Why would it diverge?
Compare with 1 over a radical n.
Yeah, compare it to 1 over radical n. So n equals 0, okay, and we compare to 1 over radical n, right? Okay, and so, well, that's the same as, okay, I'll call this a sub n, I'll call this b sub n. Okay, that's the same as 1 over n to the 1/2 power, right? And what type of series is that?
A P series?
Yeah, that's a thing. Yeah, that's a p series. Okay, so that's a p series, and p is less than 1. Okay, so p equals 1/2, which is less than 1. And so what happens with the p series that's less than 1? Diverges, right?
Divergent.
Yeah, thank you. Okay, so this thing is divergent. Okay, but does that tell me that the 1 over n plus 1 is divergent? No, not yet. Okay, we have a little bit more work to go. Okay, this thing is always smaller than what we're comparing it to, which is kind of bad for the basic comparison test, because we have 1 over n squared, 1 over square root of n. We're saying that thing diverges. Okay, it just keeps growing. Okay, maybe it will look like this. Okay, it just diverges, it keeps growing. Okay, 1 over n to the 1/2. Okay, summation. And then this thing's always less than, okay, it starts off at 1, whereas this thing, we actually have to start off at 1 too. But this actually starts off at radical 2 over 2. Okay, because we have to back it out a term, because I can't divide by 0. But this thing might diverge as well. It just might diverge a tiny bit slower. Okay, and so I can't use the basic comparison test because it's going the wrong direction. Okay, if this thing was smaller than this, and I'm sorry, if this thing was bigger, if A sub n was bigger than B sub n, then I could use the basic comparison test. So what I'm going to want to do here is use the limit comparison test. So the limit comparison test tells me that as n goes to infinity of 1 over radical n plus 1 over 1 over radical n. Okay, and I don't think I need absolute value parts on that. Okay, the ratio of that, okay, what does this equal? This equals the limit as n goes to infinity of radical n over radical n plus 1. Okay, and again, this thing just becomes 1. That equals 1, because you could bring everything inside a square root, and you just get 1 over 1. Okay, if you took L'Hopital's, I'll do that. I don't want to skip steps. Okay, square root of n over n plus 1, which is equal to the square root of the limit as n goes to infinity of n over n plus 1. Okay, which is equal to L'Hopital's rule of the square root of the limit as n over infinity of 1 over 1, which is 1, take the square root of 1, it equals 1. Okay, and so since this equals 1, since that limit is equal to 1, which is a positive constant, okay, a positive constant, then both series either converge or both diverge. And since we know that the other one was divergent, they both diverge. Okay, so that was fun. So what does that tell me? That tells me when at x equals negative 1/3, okay, x equals negative 1/3, it diverges. Okay, so negative 1/3 is not included. Okay. When x equals negative 1/3, we get a divergent series. Okay, so now let's test. Okay, test when x equals 1/3. Okay, that one's a little bit easier because it is just, it's nicer because it turns out to be an alternating series. Okay, and so we have n equals 0 to infinity of negative 3 to the nth times 1/3 to the nth, all over the square root of n plus 1. Okay, this equals n equals 0. Oh, again, yeah, no, that's fine. Equals n equals 0 of, this becomes negative 3 times 1/3 to the nth over the square root of n plus 1. Okay. Which is equal to the summation n equals 0 to infinity, there's an infinity there, of negative 1 to the nth over the square root of n plus 1. Okay, so now this is an alternating series. And so I just need to know two conditions. The first is, are all the terms decreasing? Is b to the n plus 1 less than b to the n? Well, let's see. if we have 1 over the square root of n plus 1, is that less than, okay, 1 over the square root of n plus 1. Okay, and so I'm going to cross multiply, and I get the square root of n plus 1. Is that less than the square root of n plus 2? Okay, and yeah, it is. Okay, regardless of what n is, you're always going to get the square root of n plus 1 to be less than the square root of n plus 2. Okay, for positive values of n, obviously. Okay, so that checks. Number 2 is the limit as n goes to infinity of 1 over the square root of n plus 1. Does that equal 0? Okay, and it does. We could turn this into the limit as n over infinity of the square root of 1 over n plus 1, and we could easily see that that thing is going to go to 0. Okay, and so the whole thing goes to 0, and so that checks. And so by the alternating series test, the series converges. And what does that tell me? That tells me that therefore x equals 1/3 produces a convergent series. Okay, so x equals negative 1/3, okay, is out. Let's go back up here. X equals negative 1/3. I don't like you, you diverge. Okay, x equals 1/3 converges. You're in. And so what's my interval of convergence? My interval of convergence is negative 1/3 is less than x, which is less than or equal to 1/3. And that's my interval of convergence. So there we go. Okay, I'm gonna let you guys practice that.